Okay, kids, I'm very glad to see that a good majority of you in both my AP Physics 2 classes, period A and period H, did the assignment out of College Board. Yes, I am proud of you. It's like 70% and 61%. No, it's not 100%. It should be. It should be. Why the heck didn't you do it if you're one of those who didn't do it? Why not? Okay, fine. Yeah, see how this works out for you. But anyways, here's what I wanted to do. I got an email from 2 students saying, some of these are really difficult, and blah. Well, okay. Well, let's go over some of the stuff in there. They are specifically in there. And AP loves these kind of questions. And we want you to be all prepared for the end of the week when we have our academic adventure on this unit of electrostatics. So I've already warned you about these, the square problems. So you got a positive here and a positive here and a negative here and a negative here. And you need to know what the field is here in the middle. That kind of a problem. And remember, don't confuse this. Field and force, 2 different things. Okay, they're both F words. These are good F words, okay? Field in the middle and force in the middle. And so you have to make sure you keep straight what you're trying to find, because if we want to find the field in the center, we think out of the positive and into the negative, okay, like that, out of the positive into the negative, and these are vectors, if these field vectors would add together, so overall we get this field vector when we get this field vector, and both of these field vectors are acting on that point here, and so we'd end up getting a field. This would be a triangle out of this one here. Typically, you won't get a triangle, or you want to solve for it anyways. I'm not going to ask you to solve for triangles either, but you should at least recognize that. Oh yeah, I get this acting on this point, and this acting on that point. I'd add those 2 together, and I get this overall. This is what would happen. So overall, you'd end up getting a field that would be pointing in that direction when you add those 2 together. Okay, that would be field. Now force, we'd have to actually calculate the numbers and get a value for those forces. But we've done some of those, and we will continue to do some of those this week for practice. So I'm trying to find my eraser. I'm a mess right here. There it is. Hang on. Okay, so field and force. Don't mess those up. Let's go back. Let's just try one more. We'll make it a little easier for you. Got to ease you back into this. You kids have had a rough vacation, It's been tough. So let's say that we've got these. Boom. These 4 particles. We want to figure out the field in the middle here. We go out of the positive and then into the negative. And the field here at the center would be what? Cancel is 0. The field at the center would be 0. So that would be a 0 field. That'd be kind of like being in the smack dab, the right spot between the moon and the earth, and the gravity pulling is equal on both. The fields being generated equal on both, and then you would end up having no field at that point. They'd cancel out. All right, now force. If you wanted to figure out the forces, you would have to add these up. Add this force up, add this force up, add this force up, add this force up, and that would also cancel. These forces are vectors as well. Forces and fields here would end up being 0 in the middle. All right, well, what if we had something like this? Like a 2 positive here, a positive here, a positive here, and a negative here. Okay, what about the field in the center? Okay. Out of the positive, cancel, into the negative, out of the positive, into the negative. So at this point here, we'd have an overall field in this direction, and we'd have to calculate it. If we had to calculate it, we can calculate using our field equation. Don't mess that up. The field equation, okay? E is equal to F over little q. Okay, remember that. Now, what if we had to do the forces? That's Coulomb's law, the forces. Well, these 2 forces would cancel out. These 2 would not. We'd have to add these together, and we'd use the force equation. Okay, the force equation, if we had to figure out the forces, that's Coulomb's law. We'd figure out from between. Now, here's the thing. If we have a particle in the middle, it doesn't matter what that particle is. And when it comes to field, it's irrelevant. It's like you. You are irrelevant when it comes to the field you experience, and you're not going to influence the field of the earth, okay? You don't matter when it comes to the earth. The field's not going to be changed by what you are. It doesn't matter. So when it doesn't matter what the charged particle is here in the middle when it comes to field, it doesn't matter. However, when it comes to force, it's going to matter. Like, for example, there's force between you and the earth. So when it comes to force, you matter. When it comes to field, you don't. Force is between two things. Okay? Field is generated by one thing. So you matter when it comes to force. So if we put you in the field of the earth, you're going to have an gravitational attraction to the earth. That's called your weight. So when it comes to the force in the center, you would have to know the particle here. Maybe it's a positive 1 particle. And then from there, we would do a Coulomb's law between these two particles. A Coulomb's law between these two particles. Maybe it's a -1. And then we would take those two values for those two calculations using Coulomb's law, and we'd add them together because they're going in the same direction. Okay, there's some squares. Gotta get your bell ringing. But we also have some stuff like this. AP loves these kind of problems. They want you to think conceptually about something like this. Let's say I've got this metal circle, call it metal circle A. And here I've got another metal circle, we'll call it metal circle B. And this one here, metal circle A has 1, 2, 3, 4, 5, 6 negatives in it. It's overall negative charge. This one on metal circle B, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It has 12 negatives in it, more negative charge. Now, here's the thing. Listen up. Stop drooling. Stop it. Wake up. Wake up. Pay attention. My name's Attention, and you can pay me. Pay attention. Okay, sorry. You missed the humor. Yes, you did. Nature likes balance. Okay, nature likes balance. That doesn't mean when it comes to charge, and a lot of things, but when it comes to charge, nature likes things to be balanced. That doesn't mean zero. It doesn't mean neutral. If nature can get things to be neutral, great. The next best thing is get them to be equal, get them to be balanced. These aren't balanced. This one here has twice the negative charge of this one. So nature likes balance. All right, let's say that we take this is a metal ball, we take this metal ball with like insulated fingers and we move it over because we don't want anything going to us, insulated. We want the charge, and of course metal is conductor, it's a conductor. So we take the metal ball and we touch to this one. Yeah, something's gonna happen, something special, just like you kids, special. Well, nature likes balance. There's gonna be, remember, these negatives go to the surface because they don't like each other. And if they have a chance to get away, they're going to do that. Now, if this ball comes over here and touches this ball has less negative charge. This one has more. There's more push to get away from each other and less here. Some of these are going to go into this ball in order to try to balance out the negative charge. If that happens, then let's see. How many of these little negatives would go over here to get balanced? Well, let's take out a 1 and a 2 and a 3 of them. And then add them to here, a 1 and a 2 and a 3. Now, if I do my math correctly, and I think I did, I used a calculator right here. You shouldn't see me. I was so quick doing it. I'm fast. Want to see me go to that mountain and back? Yeah. Want to see me do it again? 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, we have balance. Nature is happy, 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 happy. We're going to end up with equal amounts of charge on both of these bad layers. But not just that. Remember, these things don't like each other. And as soon as you touch them, they're going to want to repel. So as soon as we touch, these things are going to want to run away from these things over on this side. So they'll shift. Oh, did I do it? 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. They will shift to the opposite side. So if they're touched, they're going to go, oh! Well, first of all, we're going to get some jumping of the ship to get equal distribution. Yay! And then they're going to go, ew! Ah! And because they don't like each other, they want to get away from each other. So we'll get this situation where, now if we have the situation where we separate them again, if we separate them out, then they would redistribute out to the outside. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, we'll do the same thing here. 1, 2, 3, 4, 5, 6, 7, 8, 9. all right? So they would redistribute themselves eventually and get away from each other. So we touch, we shift, we go, ew, because there's still ability to go back and forth. They're going to want to get away from each other, and then we redistribute them as we move the balls apart from each other and separate those two metal spheres, and they will redistribute. Okay, that's the kind of a problem that AP likes. They like that kind of a problem. See if you can understand the concept of shifting stuff around. Let's try one more of these. Let's try another one. Let's say we have 3 metallic spheres. A is neutral, Switzerland. B is a positive 6. It'll usually be microcoulombs, but we'll just say positive 6, okay? With me? And this ball sphere over here, C is a negative 2. Okay. What's going to happen when the following happens? What will end up being the charge on these things when we do the following? Take this ball, touch it to this ball. This metallic sphere, touch it to this metallic sphere. Okay, charge, going to strip. Now this is down by 6. You can think of it as an electron. Maybe it's a charge of positive 6 overall. So this is it's down by 6 electrons to be neutral. Remember, nature likes neutral. If it can't get neutral, it likes balance. So we can try to have this one touch this one and get these things to be neutral, but that's not going to happen. Well, why not? Because there is some charge in here, and this is nice and balanced over here. This is neutral, so we'd have a situation something like this, or we'd have equal positives and negatives. But if I touch this metallic sphere to this one's positive, and these negatives go, woohoo, I like that. And so we're going to get some shifting of electrons into this sphere. Now, if that happens, if we gain 3 electrons, we are now at positive 3, but so is this one over here because it shifted. Remember, we had positive 6 here and 0. And so we're going to get balance. We don't have neutrality. That would be great if we get neutrality out of this. Actually, if we grounded this, you aren't going out for a week, young man. You're grounded. I grounded it. Funny. If we grounded it, then grounding would mean a path to the ground. That's what that means, a path to the ground. Or it means a place for extra charges to go. So if we had extra charges, grounding it would get rid of those extra charges, then we get neutrality. Nature likes that. But if we don't have any path for these charges to go anywhere, they're stuck where they are, and the next best thing is to get them equal balance on both of the spheres. So we had positive 6 and 0. If I shift 3 negatives to this ball, it now goes to positive 3. It gained 3 negatives. And you lost 3 negatives by shifting 3 to this one, so now you are positive 3 as well. Or the charge that's in between these two would be positive 3. And both of those would get that charge. Okay, all right. All right, now what? Well, now what happens if I take sphere B and touch it to sphere C? Okay, remember, nature likes to have things neutral, but if not, next best is balance. All right, so how would that work? All right, let's see. So this is positive 3, and this is negative 2. Now remember that negatives are the things that do the shifting. That's important to remember. Negatives shift, positives don't. So if I can touch this one to this one, let's do it in small increments. Let's shift 1 negative from here to here. So we're touching this one to this one, and let's do increment by increment. So we lose a negative here. Okay, go from negative 2 to negative 1. And we gain a negative here, which makes me go from positive 3 to positive 2. Okay? All right, so we shifted one of the negatives from C to B. Oh, we're all done? No, we're not done. We're not balanced. Keep going. Do it increment by increment. So let's take another negative. Let's take another negative out of here and shift it, because remember, it's the negatives that move. Shift it, so now this is 0, and we shifted another negative over here, and that makes that positive 1. Oh, we done that? No, they're not equal. Positive 1 and 0 aren't balanced. Close. Now, the next increment, I can't shift another one here, because this would then end up being positive 1, and this would be 0, and we're going back and forth. That doesn't work. But what if I shift remember, so in other words, what's the average of these two? What's the average between positive 1 and 0? It would be positive 0.5, right? So what if we shifted from here a 0.5 negative, and if I shift the 0.5 negative, I'll get positive 0.5, and over here, I lost a little bit more in negativity and became more positive. I shifted a half of a negative, I get positive 0.5. And if you go back to the original charges, I got to remember this, what do we have? We have positive 3 and negative 2. Positive 3 and negative 2, okay? That means the positives are up by 1. Positive 3 beats negative 2 by 1, positive 1. And we cut that in half, distribute between the two, we get positive 0.5 on both of those. So the difference was positive 1, distributed 0.5. It's another way of thinking about it. So we would end up with this situation here. And then, of course, a College Board question would say, what will they, they might say, you got these 3 spheres. Initially, this one is charged 0. This one's positive 6. This one is negative 2. A touches B. Then B touches C. Then what are the charges of, and they could ask you any ones. They could do what the charges of B and C afterwards, what the charges of C and A afterwards. That's the kind of question College Board really likes, and they have a lot of questions, and several of those, and a good number of those questions from the College Board practice problems and multiple choice had that kind of an idea that we had to shift charge around. So they like it, I like it. I hope you like it. Okay, kids, hope that helps.